welcome you all in today's lecture on mechatronics. In this lecture, we are going to talk about ABU Robocon 2019, the second part. The first part I have discussed about the problem statement as well as the IIT Roorkee team strategy for the manual robot. And today I am going to talk about their strategy, design, task performance for the autonomous the legged robot. I would like to acknowledge the team Robocon IIT Roorkee 2018-19, and I am thankful to the Bhavya Giri Goswami, the team leader who provided the discussed documentation which I am going to present. The problem statement before we start I would just like to give you a brief. So, this few slides will be repetition for the previous lecture, okay, in order to maintain the continuity. The problem statement was designed by Mongolia for 2019 Robocon, and whose theme was based on sharing the knowledge. It is related to Uruttu system of Mongolian tradition. The two robots called as messenger robot have to be made, MR1 which is manual or semi automatic, and MR2 which is fully automatic. If we look out at the background of the contest, the mission of ABU Robocon 2019 Ulaanbaatar is to deliver information fast by using a relay messenger system, which they call at Uruttu, which was first innovated in the world by nomadic Mongolians. For exchanging information in a long distance, Mongolian has been using the Uruttu system as a messenger for rest, that is feeding, replacing a horse, etc. And in some cases relay to another messenger. By using the Uruttu system, a messenger was able to travel in a distance of say 400 kilometers per day. And this Uruttu system was an important invention that opened a new door for us to exchange and share the knowledge in regardless of space. And based on this concept, ABU Robocon 2019 Ulaanbaatar is designed to promote the idea of sharing the knowledge. A match is between red and blue team, and it lasts 3 minutes at most. So, this is how the game area is. You have Kangai Uruttu and this is Kangai area, this is line 1, you have line 2, you have line 3, you have Gobi Uruttu, this is there in the Gobi area, then you have the mountain Uruttu, mountain area, and Ukai zone is here. Okay. This is the throwing zone, and this is the landing zone over here. Okay. And we have seen in the previous lecture how the manual or semi automatic bot covers the forest area and the breezes. Okay. Now, for the autonomous bot, the area which are to be covered is basically this one, sand dune, tussock and the mountain. Okay. So, these are the things. So, tussock and sand dune are basically the obstacles over here, which the four-legged is supposed to four-legged robot is supposed to travel, and yes, and then it has to climb the mountain area, and then it has to reach to the Ukai zone. So, each team has one manual robot known as messenger robot 1 and one automatic robot known as messenger robot 2. The automatic robot has 4 legs as of horses, while wheels are not allowed. The manual robot carries the garage as a testimony from the Kangai Urutu, which is the starting point. It goes along forest bridges and crosses the line 1 next to the Gobi Urutu, which is the starting point of the automatic robot. Okay. Now, after the messenger robot 1 reaches the Gobi Urutu, messenger robot 1 passes the garage to messenger robot 2 at Gobi Urutu, and once messenger robot 2 successfully receives the garage, it can go along the Gobi area. Messenger robot 2 must go by 4 legs like a horse, as I said. The problem statement has the constraint that one cannot use the wheels for it, okay, and the messenger robot 2 has to pass through sand dunes and the tussock and direct to the mountain Urutu. Now, after messenger robot 2 reaches the mountain Urutu, messenger robot 1 can enter the throwing zone to throw the shagai and must earn 50 or more points. Okay. In case the messenger robot 1 earns 50 or more point, messenger robot 2 is allowed to climb the mountain, and after it reaches the Ukai zone and raises the garage first, the team is the winner, and which is called the Ukai. So, this was the problem statement. In the last lecture, I have talked about the messenger robot 1. In this lecture, I am going to focus on the technology development for the messenger robot 2. And as you see, these robots are very good example of the mechatronic system. Okay. You have the integration of the actuators, you have the integration of the sensors, okay. You have the microcontroller controlling them, okay, and you have lot of programming involved in order to get the desired task. Okay. So, the characteristic of this 4-legged robot is that it has to be fully autonomous. It need to have the 4 legs. Its weight should be around 25 kgs. Initial dimension is 750 mm into 560 mm into 650 mm. The maximum dimension is this 750 mm into 560 mm into 1000 mm, and it is symmetrical for both sides of the arena. The mechanical aspect is a brief description of the robot developed by IIT Roorkee team, is that it is fully autonomous 4-legged robot, and each leg has 2 independent perpendicular degree of freedom and 1 degree of freedom for turning, that is for the yaw motion, and this is the solid model of the robot which has been developed, and here are the 4 legs basically. So, this is say 1, this is another one 2, this is 3, and the 4th one you have there in the background, in the back side. So, the body all the legs and the mechanism are made of proper amalgamation of stainless steel, aluminum, mild steel, ABS and PLA, that is the 3D printed part. Main criteria behind this design are the improved stability while moving rapidly, to incorporate distance and proximity sensors, okay, for autonomous navigation to detect the various parts of the arena, okay, which is only possible with stable gate walking, and to cross obstacle defined in the problem statement smoothly. So, based on these criteria, the parts were designed. So, let us look at the design and the mechanism. So, first is the main chassis. Okay. This is the main chassis actually. The actuators and sensors used here are 12 volt DC motor with say 25 by 1 planetary gear reduction. Optical encoder with 1024 pulses per rotation, and the main chassis of the body of the quadruped is made by connecting the two similar sliding layer as shown over here using a customized lazy Shushan like revolute joint. Okay. This is the single layer basically where you can see you have the idler pulley, pulleys are there, flex coupling is there, encoder is there. Okay. And this is MGN rail and the guide provided over here. Both layers are stacked and are independent to move about the common central axis perpendicular to both layer by the revolute joint. Each layer has a sliding module and a DC motor attached with a coupled to toothed pulleys which act both as driving as well as idler pulley. A timing belt is used to move the sliding module with respect to the layer structure and for to and fro without slipping, and the feedback of how much the sliding module should slide linearly is taken by a rotary encoder coupled to the free pulley using the flex coupling. Then each layer is attached with two parallel slide rails as I said for prismatic joint on 20 gauge square stainless steel plate. Sliding module, the sliding guides of both these rails are joined and is attached to diagonal pair of leg modules via trusses. These are the various parts which have been used basically. You can see the sliding module over here, you have the rotary encoder, you have the actuator, yes, you have the pulleys. Okay. So, all these things are there. Thus, each layer is attached to a slider module which is then attached to a diagonal pair of leg modules. The connection and trusses are designed so as to reduce the number of joints and reduce the twisting moment of the body while walking. Therefore, to summarize, both layer can rotate independently about common axis and the diagonal leg module can move horizontally along the attached layer via the sliding module. Lazy Shushan module is a custom made revolute joint with multiple bearings to avoid play between each rotating layers. Then there is a turning mechanism for robot to turn. Okay. So, as all the turns in the arena is either plus minus 45 degree or plus minus 90 degree. Therefore, IIT Roorkee team designed the turning mechanism with only discrete turning angles as a multiple of 45 degree in any direction. Okay. For that purpose, they use the pneumatic cylinders over here, and the turning was designed to be as fast as possible. Therefore, they used the actuation of pneumatics to turn the robot, and a single pneumatic with optimum stroke length and bore diameter is attached between the two layers, such that the body of pneumatic is attached to the lower layer and end point of shaft is attached to the upper layer, okay, both by revolute joint. No sensor is used in turning, as the design is mechanically constrained to rotate only 45 degree at a time. Thus, decreases the complexity of the robot significantly. So, here basically the principle behind turning is that robot needs to extend and contract pneumatic full stroke basically to rotate the robot 45 degree in one direction, and for the other turning for the other direction turning just change the order of the leg pair. Okay. So, this is what is done over here. So, here let us look at the stroke 1 and then we will be looking at the stroke 2. Here basically the red arrow shows the direction of the movement of the robot. So, you can see initially that the robot is moving in this particular direction. Okay. And here A, B, C, D be the leg, here A, B, C, D be the leg of the robot, and where AC you can see is attached to the one layer and BD is attached to the other layer. Now, at a time when the leg BD are at the ground supporting the robot, while AC is on the air, the pneumatic is attached, pneumatic is actuated, basically the stroke 1, okay, and this will rotate the leg AC by 45 degree, as you can see over here, which is like this, and with this one actuation this will be turning by 45 degree as over here. Okay. And for the next 45 degree, what is done is that after the leg 1, after the stroke 1, leg BD are moved upwards. Okay. Leg BD are moved upward in air. Okay. So, this BD is moved upward in air, okay, and AC are moved downward to ground to support the robot. Okay. So, this AC is moved downwards in the ground to support the robot, and now pneumatic is again actuated, that is stroke 2 over here, and this will rotate the leg BD by 45 degree over here. So, as you can see this has rotated by BD 45 degree, and thus the whole robot turns by the 45 degree. So, this is how the turning is achieved. Then coming to design and mechanism, we have the leg module. This leg module is designed such that the moving module can move up down perpendicular to the ground, independent to other leg with respect to the static module. The up down motion of the moving module is actuated by a DC motor coupled with lead screw, which is supported by bearing block at both ends. So, you can see over lead screw, and here is the ball bearings which is supporting it here. Here we have the steel pipe. While making the leg module of the robot, multiple things has been considered, okay, and these are the minimum fatigue bending, lower center of mass for the stability, fast continuous smooth motion for the greater speed, so that the task could be completed within the stipulated time of the minimum of 3 minutes. Then no load on actuators when standing still, high strength to weight ratio, and foot design as per the obstacle. The DC motor is coupled to lead screw by aluminum gears with suitable gear ratio, so as to increase the final speed of rotation of the lead screw and thus the motion of the leg. The same gear is also coupled to 3D printed gear attached to a rotary encoder to measure the rotation of the lead screw. Actuators and sensors used are you can see the 18 volt DC motor with 11 by 1 planetary gear reduction, rotary encoder 1024 pulse per rotation, and bump sensor. Okay. So, here you can see this is the bump sensor, rotary encoder, okay, and this is motor with the planetary gear reduction. Okay. So, you can see here we have the bearing module, this is the encoder gear, here is the pump sensor basically, then you have the bearing block, lead screw, nut block, and so on. On the steel pipe parallel to lead screw, a bearing base slider rail is mounted, okay, that is on the static module. The two slider guides and lead screw nut module separated by a distance so as to avoid bending moment are attached to the moving module steel pipe which moves vertically. A bump sensor is attached at the top of each module to limit the span of the motion of the lead screw nut, so that the robot automatically knows that leg is at the maximum top position now. To support the moving module more, the steel channel is also supported by a customized bearing module at the lower end to distribute the load evenly while moving. Leg feet, if we look at, the feet or the base of the legs are designed in such a way that the number of contact points with the ground are more and have more contact area, so that the stability of the bot is maintained. That is there. The more contact points with ground increases the stability of the robot, while increase in the contact area increases the grip of the robot. The design is made so as to move through the predefined obstacles such as rope, ramp as well as step with ease. Certain elastic material and rubber grips were also applied so as to increase the grip more during turning of the robot and withstand the pneumatic internal forces. The whole structure is made by welding the stainless steel pipe and using some aluminum plates for certain damping in the robot. Now, let us look at the garage gripping and the raising mechanism. So, the gripper of garage is same as the messenger robot 1, actuated by pneumatic and the spring. It is symmetrical and has the gripping hand for different side of arena. So, this is how you can see that this garage has been gripped over here. So, garage raising mechanism is designed according to the constraints on the orientation of the garage while raising. A 4-bar linkage mechanism is used to raise the garage to the required height by a large stroke pneumatic actuator, so that the orientation of garage remains constant. Actuator and sensors which are used in this one are the pneumatic cylinder for gripping and raising, gyroscope sensor is there, and a proximity sensor is there. The proximity sensor actually detects garage from MR1 and give feedback to the gripper to grab the garage. IMU sensor detects that the ramp in the end is over and raises the garage to end the task. Other electronics parts used are the microcontroller. So, Arduino Mega ADK and Atmega 2560 were used, and they have the operating voltage say 5 volt, digital input output pins 54, 15 PWM output is there, analog input pins are 16 and the clock speed is 16 megahertz. Then the DC motor 18 volt, rated torque 2.77 Newton meter, rated RPM 17,040 and weight approximately 340 grams. Then the bump switch 5 ampere single pole double throw 3 pin, proximity sensor the 3.3 to 5 volt DC 5 to 100 mm. Then the motor driver basically 20 ampere continuous current dual channel mode, PWM, UART, analog, RC servo signal they take, and the PD control algorithm along with various filters like Kalman filter and moving average were used to eliminate the noise data from the sensor signal. The IMU sensor which has been used is shown over here. These are the ratings for that: power supply DC 3.3 volt to 5 volt, gyro range plus minus 250, these are available, so many degrees per second, acceleration ranges these are available, magnetic field range this much is available, and the battery used, there were two number of such batteries of 18 volt and 5200 milliampere hour current capacity. And here are the various tasks which were supposed to performed by the messenger robot 2. So, after seeing the constructional feature of the messenger robot 2, now let us look at the various tasks which these robots this robot was supposed to do. So, the first and foremost task was that the gear is grabbing and turning on. This garage has to be taken from the messenger robot 1, then walking straight for fixed distance, it has to walk, then the turning has to be there, the trajectory control has to be there, okay, and the three obstacles which were provided in the path of the messenger robot 2, these were the sand dune and tussock and the mountain, and then the finally garage raising. So, now let us look at these tasks. Okay. So, the task to be performed by messenger robot 2, the messenger robot has to work autonomously as I have been talking to you. Okay. So, the gear is grabbing and the turning on. Okay. As the fast moving messenger robot 1 moves along the wall close to MR2, a industry proximity sensor detects the garage on messenger robot 1 and the gripper on the MR2 grabs the garage, okay, the instant when it comes to the gripping range. Now, as the gripper on the MR2 grabs the garage, the robot automatically starts moving because the garage gripping acts as a start button for the messenger robot 2. Now, walking straight for the fixed distance. Okay. So, it walks straight for the fixed distance, the robot moves in full trot gait, and you see the trot gait means that the diagonal legs, one set of the diagonal legs are to be there in the air, whereas the other set of the diagonal legs have to be supporting the bot on the ground. Okay. So, with only one pair of diagonal legs supporting the robot, while other pair is in the air. The layer with the diagonal pair of leg in the air moves to forward horizontally. Then when this pair touches the ground, the support ground support the robot, same happens with the other pair of legs. Now, each leg's feet follow an approximate isoscale triangular trajectory with the combination of horizontal motion of the layer and the vertical motion of the leg moving module, just like the extruder of a 3D printer. Now, the data from encoder coupled with pulley are used to measure the distance travelled by each layer and thus the robot. Then the turning and the trajectory control. Okay. As the robot reaches a certain pre-measured position by taking feedback from the encoder, it automatically starts its turning motion as per the arena by actuating the turning pneumatic, and direction is judged by the diagonal pair of leg in contact with ground as explained in the principle of turning. Now, for a smooth horizontal and vertical motion of leg during the whole game, the PD algorithm was used for controlling all DC motors. By mapping the reading of the feedback encoders of both horizontal and vertical movement with the actual distance travelled by the feet of the leg, Roorkee team developed various motion trajectories like say triangular for walking, trapezoidal and rectangular for obstacles, and these trajectories were there for the vertical plane motion. Then let us look at the obstacle 1, that is the sand dune. The sand dune is basically a rectangular block as you can see of this shape, okay, with 100 millimeter height or say 10 centimeter height. Robot has to go through it from the top. After the robot turns and touches the sand dune for the first time, bump sensor gets triggered and the trajectory changes to rectangular, which has more leg height and slower pace. Now, by this trajectory, robot can move through sand dune smoothly and with stability. By getting continuous feedback from the bump sensor on each leg at different heights, the robot moves slowly through tusk until all its legs comes back to the ground at the initial height. After the robot moves fixed straight distance, taking feedback from the encoder and again turns 45 degree for the next hurdle. Now, let us look at the obstacle 2. Okay. So, this obstacle 2 is actually the tussock, as you can see over here the drawing for this, the perspective projection of the 3D model for this. The tussock is a toughest obstacle which basically which is basically composed of 2 thick ropes one after other mounted at different heights at both ends and have variable slack. It was the toughest obstacle as the slack provides randomness and it is very difficult to detect unpredictable rope by any sensor. Now, as the robot turns again after the sand dune, it changes its trajectory back to the rectangular and moves slowly straight through the tussock without detecting the rope. To prevent the rope from getting stuck in robot part and corners, all the front faces of leg which will be touching the rope were made slightly slanted to slip the rope to bottom of each leg. In addition, various elastic threads were attached at bottom of the leg to divert the rope away from the robot. Now, when the robot crosses this obstacle, it has to wait till the MR1, that is the messenger robot 1, scores 50 points by throwing the shagai, and then only it can move to the final obstacle. Okay. So, this is a figure you can see the various legs, that is the legs of the bot crossing the tussock. Okay. So, this is how it was. These pictures are from the actual arena. Now, let us look at the last obstacle, that not obstacle, rather a different type of terrain, that is the mountain. The mountain is 1.7 meter long slope with 15-degree angle on which the messenger robot has to make a climb as a final obstacle. During the time when messenger robot 1 scores 50 points by throwing shagai, team member rotate the MR2 towards the mountain without making any mechanical or electronic changes. The movement MR1, the moment MR1 score 50 points, the MR2 can start moving up the ramp. For a smooth transition from flat to the ramp, initial rectangular trajectory was used until all legs are on the ramps. After that, the trajectory is shifted to triangular for faster climbing. All legs are properly covered with a rubber grip to prevent the slipping on the ramp. A gyroscope that is IMU continuously takes feedback of the pitch angle of robot and let the robot know when it reaches the final destination on the flat surface with all its leg on the top. Next, the last operation is the garage raising. Okay. As all the legs reach the top flat surface of mountain, by taking feedback from gyroscope sensor, the robot actuates the pneumatic of the garage raising mechanism. The garage is raised to the height above the robot while maintaining its straight orientation, and thus the problem statement is achieved. So, these are the members of the team Robocon IITR 2018 and 2019, and this is the trophy which they were awarded, that is the judges special award winner, and they were the quarter finalist award winner. I would again like to thank Professor Sailesh Ganpule, the faculty advisor for the Robocon team, and the various members from the third year, fourth year and the second year, all the members of the Robocon team who contributed to this very nice, useful and learning activity. Thank you.